Okay, lesson 11 for, let me go ahead and share. This is lesson 11 for those who missed class today. I know there's a couple of you out there, at least 4 or 5. So I told you I would go ahead and put this on video. So that's what I intend to do. So this is what we talked about in class today. The only thing you won't get is sort of a feedback and seeing kind of how you guys react whenever I say stuff. So, and here it is. So today what we want to do is two main things. I want to implement ridge regression and Lasso and scikit-learn on 2 different data sets, and I want to conduct k-fold cross validation, validation using scikit-learn. So that's what we end up doing. Before I get too far into it, I just want to review what the loss functions look like for these different methods. And so if we're doing OLS, right, so you'll see OLS when we get down to it, ordinary least squares. The loss function is just the same one we've been working with. The only thing we added last lesson was a ridge component where it had this, and I think I used a lambda in the last video, but we're going to use alpha today only because scikit-learn uses alpha here. And basically what you're doing is trying to minimize the parameter values, all of them except for the 0th one. So you can see that. And then so this ridge has a square term on it. So if you remember, if it's a square term, then that's the constraint, looks like that. And if it was when you get down to Lasso, that constraint look like the diamond, right? And so they do different things. There's different constraints on this optimization, but just go back and look at last class, and you can kind of see what's going on as far as the mathematics go. Today we're actually just going to implement it. Okay, so let's get started. Some of the new stuff I'm going to just sort of point out here. So this train test split is just a function inside the sklearn, so scikit-learn model selection package. And then you get your linear model. So we got linear regression. We got linear model called ridge. We got one called Lasso. So I can pull these out and I can use them in my code below. So after I pull them out, I'm not pulling in the entire package, the entire scikit-learn package. I'm just pulling out the functions that I'm going to need down here. Here's another thing that you can do if you really want to. If R2 score, so this is what I've done. I've pulled out the R2 score function, but I've called it R2. So below, when you see me use R2, what we're talking about is the R squared. So I'm trying to find the adjusted R squared. I'm just going to show you that what it's equal to in the stuff below. All right. So just note that a lot of that stuff that we're pulling out is up here. There's the k-fold piece that I'm gonna add to it, but I won't do that until we get there. All right. So with that data. Let's look at kind of what's going on here. So you can see this data is linear. So what I'm trying to do in this first data set is show you it's kind of hard to squeeze a little bit more juice out of a set of data that's already been modeled pretty well, right? So this is pretty linear, this is pretty linear, and this is kind of all over the place. What we'll do is we'll put a couple nonlinear terms in there. Let's see, an interaction term. So one interaction term would be df. So all I'm looking at is, this one's linear, this one's linear. So if I put an interaction between those two, maybe we'll get something cool out of it. So this can be TV underscore radio. And all I'm going to do for an interaction term is I'm going to say TV times then I'm going to use a for loop. So for I in range, I don't know, 2 to 6, I think is what I use. So 2 to 6, and then I'm going to then create new columns of data, or so we're creating data basically. So TV plus, what is it, str of I. So that'll be TV2 or TV3, TV4, all the way to 5, and then I want it to be df TV to the whatever ith power. So when it's a 2 is squared, when it's 3 is cubed, and so on and so forth. And then I'm going to create this column called radio, and I'm going to add stri to it. Same thing, radio, and then to the ith power. Finally, newspaper. I equals df newspaper. And if you haven't figured it out yet, I'm trying to really fit this, overfit the data. That's what I'm trying to do. I don't know if we'll get there. I don't think in class we did, but let's look and see what this does. And if you see, TV's 230, then newspaper 2 should be 230 squared, and TV 3 should be 230 to the third power, and so on and so forth. So we have 17 columns now of data. So now what I want to do is I'm going to set this data up. And the way I'm setting it up is I'm going to pass it into these functions. So all of these things that sklearn are going to do, I'm going to pass them all in as a data frame. So I'm going to set let response be, and in this case, I forgot to explain. If you don't remember, we're trying to predict sales using TV amount money spent on TV, amount spent on radio, and amount spent on newspaper. So my response variable is sales, and I'm going to let capital X be df. It should be .drop. So I'm dropping everything. I'm dropping the response variable out of there. X is equal to 1. I don't. So my X should be my predictor variables, and in this case, I don't need the response cell. I don't need the column of cells in there. So that's all that does right there. And then, but I do want for Y, I want that to be df response. Press shift enter. Let's look at what shape is. So shape 16. Remember, this was 17 columns, but it had cells in it, so we took that cells out, and now we have 16 predictor variables in here, and 16 different coefficients that I'm gonna let sklearn find us an answer to, right? So I've got the stuff here. Before we get there, though, we gotta split it into. So again, this is the new part that we really haven't talked about yet. Is when you're given a set of data, you don't want to use the entire set of data in order to train a model, right? So what we want to do is hold a certain percentage of that data off to the side, develop the model with one part of it, and then use the second part as our sort of our validation of the model. So run things through the model that the model hasn't seen yet. So that's kind of what you're trying to do, and that's what the sort of the intent of this class is. So here, in this case, how do we split it? Well, remember that that function that we pulled out here called train test split. So I'm gonna just copy that one, put it down in here, and say, I got to remember, I think it's train x, test x, train y, and test. That function, and then I'm going to pass in my x and my y, right? So, and what this is taking, it's taking that x and it's splitting it up into two pieces of data, and it's taking that y and splitting it up into train and test. And then you got to tell it how much. So how much do I want it to do? I don't know. Test size is equal to 0.2. In this case, that means 20%. And then if you want to be able to reproduce this, you got to give it a random state. It's kind of like a seed. And I'm going to let it just be 1 for right now. And now I think we're ready. So I'm going to have this object called OLS, ordinary least squares, and it just says, hey, use linear regression, and then fit it using the train and the train X and the train Y. That should make sense to you. And then we're going to use so after so this is a method. This fit is called a method, and it needs data in order to fit it, right? So it's going to use the techniques that we've talked about already in class. And what this does is what OLS.predict does is it send in the test data and then give me what y hat is, right? So this is the test y hat, I should say, not the train y hat, but this would just be the test, and then we can use it to calculate things. Okay, so shift enter, and you can see you get a pretty high, and this actually is adjusted R squared, 0.99442. I mean, it's pretty high. So what we're going to try to do is, but that's not what I'm interested in. I'm not super interested in how the model modeled against itself, against the data that used to train it. What I'm really interested in is how much or how well it's doing against this test data that the model hasn't seen yet. So what I'm doing now is I'm taking OLS underscore y hat. So this is so that's that R2 function that we pulled up before. This is called R2 score, and I said bring it in as R2. So this is R squared. So all I'm trying to do show you here is that these two R squareds are match up. This OLS.score gives you R squared. So we're not going to use this R2 anymore. I was just kind of showing that it is the same. And then if you're interested in kind of what the coefficients look like, so that's how you get to the coefficient. So dot coefficient, and that will give you a NumPy array, and then dot shape tells you what the NumPy array looks like. And if you want to know what the coefficients are, you can just back up off this and hit Shift Enter. I forgot the code. I had to leave that there. So these are all the coefficients. So what you would do is you take that number right there, multiply whatever's in column 1, this number times column 2, this one times column 3, and then you add them all up, and then that's what would give you y hat. And then what this number does, obviously, is it compares the y hats to the actual y's, or in the test y's, I should say. So it's doing what we needed to do in order to calculate SSE, SST, and R squared. All right, so the point here is I would like to use ridge regression and squeeze a little bit more juice out of this thing. I mean, I know 975 or 976 or whatever it is going to be pretty hard to beat, but let's see what we can do. So I'm going to copy this, Control C up here. I'm going to put it down here. I no longer need this y hat anymore, so I'm just going to take it out. The reason being is because I'm not using this function. I'm just going to let the score function do its business. Okay, and so let's call it ridge. So I'm just going to change all these OLSs to ridge, and we want to get rid of that. We're going to use the ridge function that we pulled in already. We got to give it an alpha value. I think this is alpha 0.001 or something like that. Might work pretty well. I've experimented with this a little bit, and we're going to say normalize equal to true, and then ridge dot. So again, the ridge is now an object. It's this it's this regression object, and then I'm telling it to fit. I'm using the same training data, and then I want the same score to pop out. This is the adjusted R squared on the training data. Let's see what happens. And then I want the score for, so 0.98 isn't as good. So if you were just comparing, say, how your data did on the training data, then obviously we wouldn't want to use ridge. But the issue here is that's not what I'm interested in. I want to know how it's doing on this data that it's never seen before. And so that's when you would go ridge dot score, and then we'd have test X and test Y. This is the one I'm interested in. So, I mean, it's hard to squeeze any more juice out of having an R square, just R square of 976, but it looks like we got a little bit more out of it. So, and that's a good thing. And you can do the same thing with Lasso. Let's go ahead and do it. Control C, Control V. Now, again, I'm going to change everything to Lasso. Lasso. I think Lasso is going to be a little bit better, but we'll see. And then insert again. R squared on the test data is not as good, but remember what it's supposed to be good at. I'm gonna do tests Lasso. Ooh, it got really well, right? It did almost as good as the R squared on the actual data here, right? So R squared actually went up. Just R squared went up when you went from the train to the test. And the neat thing about Lasso, and I don't know if I pointed this out, is that Lasso will zero out many of these parameters that aren't needed, right? So these predictor variables that we just don't need anymore, Lasso is going to come back and tell you, well, you need this one, you need this one, you need this one, and all of these. And again, we could go back and figure out which ones of these, that's a pretty small number anyway. And that's a 0, so it looks like 1, 2. Again, it's Lasso kind of does, as opposed to ridge, where I think if you looked at the ridge, matter of fact, let's look at those. All of them are going to probably have a coefficient, but they're going to be really, really small, right? And this would be the ridge one, so I can make sure that you got that. Again, it's smaller numbers and probably in the same ones that were Lasso was going away. Okay, all right. One data set down. So I've done this data set. I fit it to ridge. I haven't done k-fold means because I'm not super interested in this. I mean, do what you want to with it. The next one is if we tried to use So this is cadet performance. The data has been dehumanized, so you can't figure out who's who. But I have this information, this data on cadet performance. And suppose we want to try to predict MA205 numerical scores, given some plebe year performance, some high school information, and maybe general information such as your major. So this is actual data. So I'm gonna this first piece. So we're gonna pull in the data, and then we're gonna plug in a 97 and 93 and so on and so forth for these different grades. Shift enter, and then I think this function is pretty cool. Maybe you guys won't, but I think I get this from Colonel Lindquist. But I think it's good to look and see. Okay, so that's a qualitative variable, and it only has two possible outcomes, right? You can either be a yes or a no, or whatever they are. It doesn't tell you what they are. Here's another one: prior servers, yes or no, true, false, and so on and so forth. Let's see, gender, 2 of them, and combat veteran, 2 of them. Oh, here's one, major. So there's 116 different majors. So this kind of gives you an idea when I get to start looking at the data, why we have so many columns. 116 of them are going to be those columns called a major, and we'll talk about why. You probably already know why because we've already talked about that in class. Again, another useful thing to kind of look at all of the columns in the thing is this thing called info, and you can see if you looked here, there's one English grade that didn't get pulled in, and so I'm not going to drop that piece of data. I'm going to just put in the mean in for that null value. So I looked at columns. So what I did was I grabbed this, right? So I copy pasted this down here, and then I deleted all the ones that I didn't like or I didn't think were useful. For example, like cadet ID. I didn't need cadet ID to try to predict what the person's MA205 grade was. I did like SAT math. I wanted to use SAT verbal. I didn't know CAPS, gender, CFA, that's your cadet fitness assessment, I believe, community leader score. So I just wanted to look at all these and see what would happen. So shift enter, and you can see this is now, instead of, it has 17 rows instead of, I'm sorry, 17 columns instead of, did I ever print that off before? No, I didn't. Oh well, maybe I should have hit DF here, but no, this will tell us how many data columns. 20. Oh, so there was 26 columns, and now I only have 17. All right, and you can do the same thing with the unique and the info and kind of get all it. So again, we can look through here. We still only have 1754. I have a one null value running around in there, and this is the next thing I did. I would encourage you to do this. I mean, I just printed off all the columns. These are the useful ones. But now what I did was I copy pasted this down here, and then I changed it to whatever I wanted it to be. So prior service. I don't want to type in prior underscore service every time. I just put PS. I don't like doing that underscore old business, so I just put math and so on and so forth. So I would encourage you to sort of make it do whatever you want it to do. As far as like, especially if you're going to do some exploratory data analysis, some EDA, if you're going to do that, I would definitely want to decrease the amount of stuff that you have to type in order to get the stuff up that you wanted. All right, the next thing is that I put in was an interaction term, so I shift enter. And there's lots of interaction terms that we could have done. I mean, maybe this wasn't the greatest one. Maybe I should have put in an interaction term of, how about DF? I'll just put another one. This is on the fly. I'm going to call it cat. Oh, no, I'll tell you what. Let's wait until after the next one in order to figure out what our terms are going to be. So shift enter. So now I'm going to come down here. I'm going to look at this heat map and at MA205. I'm looking for high numbers here, or very low, numbers close to absolute value of 1. So 7.6 and 7.6. I'm going to put an interaction term of MA104 grade and CAPS. I don't know if that's going to help us, but we'll see if it does. So my interaction term is DF. I'm going to call it CAPS. CAPS 104. How about that? CAPS 104. And that's equal to DF CAPS. I think that's correct. Is it underscore? Yes, all lowercase times DF MA104N, I think. Yeah, so that's what that sucker is. And then in this one, so the one fill in A, the one number, what you've probably seen most of the time is a 0 here, but all I'm doing now is I'm putting in the mean of whatever the English 101 scores are, right? So I'm just replacing that, shift enter. And then if you want to look at df info again, df.info, you can see that caps is 1755. I mean, all of them are 1755. There are no null values anymore, right? So I'm going to just erase that. And then the next thing I'm doing is turning in WCS, which is the whole candidate score. I'm going to turn that into a float. And then the reason why I did that is because this thing right here, this WCS, when I go up to maybe the 5th power, it starts getting out of hand in the integer setting. So I wanted to turn it into a float. Shift enter. And you can look over and see, look over to this right here, and you can see these 5th order. So again, I'm trying to overfit it and let ridge regression kind of take away, or lasso take away. All right, I think we're at a spot now where we can now put our data, create our data frames that we're going to use and when we start to split into the test and the train data. So, one other thing. The first thing I'm going to do here is do something that the stats models we've already seen before in the past have taken care of us. They've taken care of these things called qualitative variables, right? So right now I have a qualitative variable for turnback, right? So it's either a Y or an N, and for this PS I have a Y or an N prior service. Let's see. Oh, major is a qualitative variable. There's 116 of these suckers. So what I'm about to do is I'm about to create dummy variables for each one of these. So I'm going to have 116 columns, and I'm only going to have a 1 in one of those 116 columns. So that 1's going to represent the major that the person's in, right? So whoever this first guy is a foreign language major French, we're going to put a 1 in that column out of all 116 of these, and they're going to be zeros in all the other ones. So it's called a dummy variable, right? So all the other ones are sort of dummy variables, except for the one that has they're all dummy variables, but there's only going to be one in each one of them. This one's going to produce 2 columns that I have either a 1 or 0 in it. Actually, it's going to, I think what happens is it produces 1 column and it's either a 1 or 0, and this one actually would have 115, and one of them would actually be missing. No, I'm not going to go through any of those details, but this thing is called this function. So because sklearn doesn't handle it, and because you need this quite often, pandas, the data frame folks, have created this thing called PD. You'll be surprised what the name of it is. It's get dummies. Get dummies, and what that does is you pass in your data frame. So this is going to be my new data frame called data, and that's my old data frame that has the qualitative variables in it. This new one's only going to have numbers in it, and because I'm going to tell it to drop underscore first equals true. So I want to drop the qualitative variables and only have numeric variables. And then we're going to do the same thing we've done before. We're going to pick a response variable. In this case, it's MA477 And then I'm going to do, we could literally go back and copy paste exactly what, except for data. That's true. So X is equal to data dot drop instead of df dot drop. And I'm dropping response, and I'm dropping the entire axis equals 1, which means that I drop the whole column. And then Y is going to be equal to data response. That's right. Let's see what happens. So there's 35 columns in here, so I'm expecting this thing to be 35. No, I'm not. I apologize. 35 columns here. I'm expecting to be much bigger because I know I have at least 116 of these guys running around in there, and then I got 2 of those, either 1 or 2 of those. We'd have to check it out. Let's see. Oh, yeah. So turn back Y. So it looks like turn back underscore Y is, so if it's a 1, then it's a yes. If it's a 0, then it's a no. So that's what happened. It's however many unique values are in there minus 1. Okay. Dot shape. 1755 by 148. All right. Now what we want to do is we're going to take this X and separate it into train X, train Y. I don't know. test x, train y, and test y. Equals to train test x comma y comma. In this case, I'm going to let the test size be 30%. Because we have more data than what we had last time. And then random state equals 2. And then OLS is equal to linear. I'm just going to copy that. Let's go back up here where we had that before. Right here, Control C. All right, so this is regression. I don't need this one anymore because I'm not going to calculate it. Let's find out what happens here. So I got a 0.62. And then OLS dot score on the test data. So test X and test Y. Okay, so it's 0.62, and then it went up actually. So it's not horrible, I guess. I was trying to overfit it, but I don't know. Maybe it looks like we didn't overfit very well. Again, I'm going to go back up here and grab the ridge stuff. So ridge, lasso, ridge, Control V. I don't think this is a very good one, so I'm gonna share ridge, see what happens. Oh, look at that. And then insert this one, E, and I'm gonna call this ridge.score on the test stuff, on the test data. So it went down to, so it went 0.72 on the train data, and it went down to 6.8. So again, I'm comparing this number to the test, so 6.3. So it went by 0.05, which I'll take that. Again, we haven't really explored how good this is. We're going to do that here in a second. And the last thing I'm going to grab is Lasso. We've already done Lasso on this one up here. It's previous, and as long as your names are the same. So notice how train X, train Y, and test X and test Y are all the same. Then you don't have to, retype in all that stuff, right? The code's going to be the same. And I think 0.73. Let me add a spot here for lasso.score test. Ooh, so yeah, so it looks like we're doing pretty good. I mean, that's not a horrible R squared, but we definitely got an improvement over the ordinary least squares. Okay, so your next thing, hopefully your next question is, well, how do you sort of look at this alpha business, right? So how do we get a decent alpha? And okay, so we'll just kind of experiment with that. So alpha is equal to NP dot a range. And if you don't know what a range does, just go check it out. I mean, just take a second to. It does the same thing as the range function does in normal Python. And then I'm going to give it a step. I'm going to step by 0.1, and then for a, oh, I got to tell it RSQ. So R squared is equal to some blank. So I'm going to collect these things, and I'm going to say for a in alpha. Then I want to do exactly the same thing up here. So ridge regression. So it's this one. E. Ridge. The only difference is I don't want alpha. I wanted alpha to be A, right? Because I'm grabbing an A out of each one of these suckers. And then ridge.fit. So I'm putting that back in, and then my score is this one. Test and test. And I just don't want to print it off to the screen. I actually want to capture it. So how do we capture it? RSQ.append. And I'm going to plt.plot. Let's see, the x-axis will be alpha, and the y-axis will be that RSQ that we just calculated. Let's see what happens. All right, so you can see that 0.2 is pretty good. Is that the one that I used? No. Shift enter, and 0.6855 is the highest that we can get. 6855 is probably, I mean, you could go in between these two, maybe in between these two numbers, and maybe there's something that pops out, but just know that I'm not going to do that. I mean, it's not super important. I mean, you want to get a good alpha, but you don't necessarily have to get the best one ever. Again, I feel like you're overfitting if you start doing that. All right, so let's do the same thing. Control C, bring it down to here. What the heck? Control. Oh, maybe I had the control button down. Oh, that's probably what it was. I did something with my willy there. All right, so now I want to find the best one for lasso. I'm going to let that be 0, 0. I'm going to go to 0.1, and I'm going to go by 0.001. 0.01. I think that's what we need to do. And lasso. But I could be wrong. I mean, if it's not, we'll change it. All with sticking in here and find out what happens, and then go. Thing is in there. Yeah, 0.004. Is that what I used up here? It is not. Shift enter, shift enter. Oh, and I got a 0.69. So lasso looks like is doing pretty good. All right. So the last thing that I want to do is this thing called k-fold validation. So what you're doing in this sort of validation, the only thing that Python's doing that's going to do for us is this. So suppose we got this set of data here, and right now what we've already done is we've taken, so pretend like for a second these are indices in the data, and what I've done is I've kind of randomly put them in here, right? So I'm taking about 10 or 30% of the data. That's what we did. We took about 30% of the data, and we set it aside to do what's called a test, right? So I used this other data down here to train. So we've done that once, and we've calculated. So we took this, we calculated R squared, and we said, hey, we obviously like a high R squared. What we're going to do with k-fold sort of cross validation is I'm going to do this sort of the same idea, except we're going to do it many times, and that's gets back to bootstrapping. And there's some things that you can do with bootstrapping that's beneficial for you to kind of. So what we want to do is really understand what's going on in this model, and if you can do it this way, if you can do this k-fold cross validation, then you can get a pretty good understanding of what's going on. So for what this problem is doing, so I've taken maybe this might be your first set. Again, imagine that this is the set of data and they're all sort of jumbled. They're all sort of random, and these are all random. So this is the same set, right? So what I'm doing is I'm going to, if n is equal to 10, that's what it will be here in a second. If n is equal to 10, then I'm going to do this 10 times. I'm going to make this a tenth of the data, a tenth of the data. This will be a tenth of the data. And we'll just keep doing this, keep breaking this data up into these random little pieces. And then what I'm going to do, again, I'm going to use the part that's not sort of blocked off in red. I'm going to use that part to train my data. So this will still be trained down here. And then I'm going to use this, and I'm going to calculate what's called the mean squared error. So all mean squared error is y hat minus y squared, and then divided by the length of y. We'll say n. So we're going to capture this mean squared error here. We're going to capture it here. We're going to capture it here with this randomly chosen indices. And then at the end of the day, if we have 10 of these, here, let me maybe put that. So maybe we have 10 of these suckers. We'll have 10. And then I have 10 MSEs that I'm going to now average. And what I'm trying to do is get the true value of how much error is really in this process. If my model, and what I'm trying to do is make it small. So we want to make it, so I'm going to call it MSE bar. We want to be as small as possible. Okay. So that's what we're going for. So we'll jump back over in Python and we'll implement this in Python. So import, what's it called? Import, so from, it's not import, it's from. So from sklearn dot model selection. import repeated fold. So that is a it's an object in this sklearn model selection package. And then what we'll do is we'll create, it's a class, I should say. So then we'll create an object from that class. So RKF repeated K fold is equal to, and I'll mess that up here in a second when I go. I'll probably put RFK because there used to be a stadium in the NFL called RFK. Okay, so RFK is equal to this repeated K fold n underscore splits. It's the number of splits. So like before we said it was 10, I'm going to let it be 10. So I'm going to split the data up into 10 as equal as possible test data, right? So that's what we're going to do, and that's different for each one of them. And then you can do it multiple times, right? So in other words, it's certainly a random, so n repeats. I'm going to let it be 1 for right now. I'm not going to do multiple of these, but just understand that I could just put a number on here. If I did put a 2 here and a 10 there, there would be 20 of these. But the first 10 would all be sort of mutually exclusive test data points. And then you go back and do a repeat, then you'd have 10 more mutually exclusive test points, and so on and so forth. You could just keep doing this. So and you probably have to experiment with this to understand what's going on. So MSE is equal to that. So for train index, comma, test index. And that's really what this repeated FK fold object or class is doing for us. It knows, so when I created this RKF, it knows to go in there and split the data up into 10 spots. In other words, like the data that's in the first set is different than the test data that's in the second set that is different than the test data. Like I said, mutually exclusive. In RKF. This is a method inside that object, and I got to pass in the data. So so this object knows how much I want to split it, give me the data, and then it'll do it as best as it can. When I say as best as it can, there might be one that's different than in some of the other ones. In some of the other ones. So then I'm going to have X train, comma, X test, X.ilock. So you got to use ilock in this one. If it was a NumPy array, you wouldn't have to do this, but remember we passed it in as X was a data frame, and then give me all the columns in that sucker, and then comma X.ilock X, give me all the columns in that one, and Y train Y test. I am in the middle of creating a video. So this is train index, I believe, right? So that's all this little thing is doing, is it's creating this thing for us. Train index. Okay, and now what we can do is print this or do this. So OLS is going to be equal to linear regression OLS dot fit is now. So we're doing the same thing we did up here, right? So up here we did it once, but down here in this thing I'm doing it multiple times over lots of different data. So OLS dot fit would be X train and Y train, and then OLS. We need that OLS Y hat now, and the reason why we need that is because I'm going to calculate the MSE by hand, basically, and that's OLS dot predict, and then I got to pass in X test. So now that I own that, I can do MSE dot append, and I think it needs a bunch of these suckers, right? Because I got the append is going to be on the outside, and then I got to go y underscore test. That is the thing that we're trying to hit, and then I got this OLS underscore y hat. Then I'm going to square each one of those, and I'm going to sum each one of them. And then that should be the end of the pen. Okay, and now I want to print MSE. I want to print MSE, I'm sorry, NumPy array. I'm going to turn it into a NumPy array and then do MSE dot mean so I can get happens, and of course y dot oh, it's capital Y. It's not a capital Y. It's an underscore Y. We got discombobulated there for a second. MSE blah blah blah. What did I do wrong? Operands. Okay, so obviously I'm trying to pass in y test. Well, that's y hat. X test. X train. Oh, here we go. Y train, Y test. Oh, there we go. There it is. Again, I got probably discombobulated. All right, there we go. That is not good. That does not look good at all. So why is that so horrible? Oh, I forgot to divide by. Okay, never mind. So this should be one of these needs. Yeah, right there. I'll do it right here. Divided by length of y underscore. Is it test? Yeah. Okay, that's much better. I knew it was around 29, 28, something like that. So this is k-fold. So think about what this is doing. So each one of these that's getting printed out here is a different set of test data, and they're all mutually exclusive. So I got, you know, a set here that I'm doing with because again I broke it up into tenths, if you will, and said, all right, give me a tenth of the data, take it out, and use it as a test. And then it gives me an MSE calculation. And it does the same thing with a different tenth, and then a different tenth, and so on and so forth. And then I'm using all of these in this average here to come up with what this model is basically doing. Now, if I did it, I don't know, if I did it many times, I could do it with 3 repeats, and we can get something like that. And I would have 30 of these suckers, and we're getting something close to what it was before. Anyway, so again, that's what we're trying to do. I'm gonna just do one more. I'm gonna do the lasso one. I'll leave it as an exercise for you guys to do this one. But the lasso one would, okay, so let me make sure I change everything. So the only thing that we're doing up here is creating those indices. And then down here, this should be, I'm just gonna go grab the lasso. All right, I think that did it. So, oh, I got to give it a thing here. I forgot what the lasso was good at 0.04. 0.004. And then this will be lasso y hat, lasso project. And then hopefully, oh, no, right here, I need add. I should have just called that y hat, and then I wouldn't have to change that everywhere. Let's find out what happens. 22.404. Yeah, so you can see that that this one's a little bit better. Again, the cross validation is just something that you want to do to make sure that you just get lucky on the one. You know, up here you could have got lucky that that your train test split did a pretty good one, so that you got a really good score down here. This one really sort of makes sure that you know, you get the best model for you. Okay, well, that's all I have. Hopefully you guys got something out of this one, and I will see you next class. Again, this is for the people who missed this class, or if you just didn't get it the first time. There is a homework exercise in this one, so don't forget that. Make sure you go back and just do kind of what we just did for this, using that soul bike data set. All right.